Hello, I'm Barry Sullivan, Program Director for the Electrical and Computer Engineering Department Heads Association, and it's my pleasure to introduce this spotlight presentation by EMONA TIMS. The presentation will be on hands-on learning and presented by Carlo Manfredini. Carlo?
Good morning, everybody. Thanks very much, Barry, for that introduction. And I'm very excited to be here, especially when I heard that the talk was going to be here in Napa Valley. I thought it is so close to home. It's just merely a quick 14-hour flight and then just a short drive up the road. So I thought I got lucky because my other colleague got sent to a show in Kazakhstan. So I thought Napa Valley, Kazakhstan, you know, I think I did pretty well. Having said that, I did go to Kazakhstan last year, and it was actually very interesting. Very unusual, a bit different, but I'm happy to be here with you all. Finally you're thinking, okay, Manfredini, Italian name, Australian accent, and a company called EMONA TIMS. What does it mean? What does it represent? So let's have a quick look at who EMONA TIMS are. So EMONA is actually the Roman word for Ljubljana, which is the capital of Slovenia, which is where the founder of EMONA Instruments, Fred Bresnik, originated from. He set up EMONA Instruments in the 70s, and we are Australia's largest test and measurement instrument supplier. TIMS stands for Telecommunication Instructional Modelling System, and that was developed by Tim Hooper at University of New South Wales in the 1970s. And he was trying to address the problem of how to teach the many topics in telecommunications with only one piece of lab equipment, and how to keep that up to date as it continuously changed. So he came up with the idea of TIMS, and then in the 1980s we worked together with Tim Hooper, who is actually my lecturer at university, to commercialise the product. So since 1988 we've been manufacturing the TIMS product range, and we're now in more than 40 countries around the world, and more than 165 universities in the US alone, very many prestigious and well-known institutions. So my assertion is that technology changes and yet principles remain the same. So I have a little timeline here relating to that, and some of you may remember the beginnings of information theory. I don't know if you want to date yourselves, and so back in the beginning, you know, we had the transfer of information, and then, you know, technology moved along, and we have valves. They were the next big thing. And I was watching a YouTube video by Dr. Robert Gallagher at MIT, and he was told in the 50s, listen, information theory, it's dead, forget about it, just stick to studying valves. Now, fortunately, he didn't do that because, you know, time moves on, and valves are now have been put away, and now we've moved on to you know, so transistors have come along, and but nevertheless the implementation in the theory hasn't really changed. And so I met another professor, and what he would do in his labs is get students to build AM and FM circuits with electronic components. And whilst that's a very interesting and hands-on way to teach students, the difficulty is that there are so many topics to cover that it's very difficult to get a lot done in a short amount of lab classes. So, so these days, you know, the technology has got FPGAs. So FPGAs are everywhere. What's inside them? What's inside these things? Well, here's a typical example of what's inside. There's block diagrams, and inside these FPGAs there are filters, and there are multipliers, and there are phase-locked loops and VCOs, and very many elements of block diagrams. As well, a professor at Purdue told me that what else is inside them is magic smoke, and it's very important that you don't let the smoke out. Otherwise they won't work anymore. So keep that smoke in there. So, this mouse is going to be in trouble. No problem. All right. Okay. So how about the future? What's coming? Optics, quantum, I don't know. That's the kind of things that you'll be discussing at this conference. But regardless of what's inside, what kind of technology we're using, they'll all be implementations of block diagrams. So where do the block diagrams come from? Well, they come from the mathematics. They are basically representations of the maths. So here we see the maths for QPSK, very basic mathematical formula. And that can be represented by the block diagram for QPSK. And what we do at TIMS is for each block in the block diagram, we have a hardware module. So each module represents one block in the block diagram. So if we have a look at that, if you have an oscillator, we have an oscillator module. If you have an adder, we have an adder module. A multiplier, we have a simple 2-input multiplier. Phase shifter, sequence generator, bandpass filters. And then, of course, we have a large number of different modules with encoders and demodulators, etc., etc. So we have more than 60 different modules which are patched together to implement block diagrams. So what does this look like? Here we have a student, for instance, using a couple of simple elements to build up an AM circuit. If you're looking closely, you can see he has an adder, and he has patched the adder to the multiplier. So he's adding the message to some DC. He's multiplying it by the carrier. Now, what's kind of unique about TIMS is that we call ourselves a modelling system, which basically means down there you can see the 100. The carrier we use is 100 kilohertz. So rather than dealing with real RF frequencies and the complexities associated with that, we basically build the telecommunication systems around a carrier of 100 kilohertz. So in that way, the student can see the carrier and the baseband signal on an ordinary oscilloscope, and it allows them to have a good and thorough intuitive understanding of what's happening to the carrier in the modulation process. So that's a very, very simple introductory example. A more complex example would be something like this, where we have a digital signal in a noisy channel. And so over on the left, we have we build the baseband transmitter. Then we also build the channel. Then we build the receiver with a couple of modules. And then finally, most importantly, we build bit error rate instrumentation. We don't just have a push the button and find out what the answer is type approach. We actually get the students to receive the data, make important decisions using an iPattern display, and then compare it with the incoming data using exclusive OR gates, and basically really getting a true understanding of what does bit error rate measurement really mean. And in this way, one of the professors said conceptual difficulties evaporate within minutes of a TIMS experiment. So if we have a closer look at that, brief video here. So here you can see. So there would be the noisy signal coming in. You can control the levels of the noise. You can control the SNR, take measurements by putting modules in and out. And depending on the complexity of your experiment, you can have another rack. And so the students are taking control of the experiment. They're actually building the experiment themselves in a way that's intuitive and encouraging to their learning process. So how many topics can you cover with this single system? Well, I'm just going to whiz through a list of experiments. These are our capabilities listed by wireless standards. So on the left, you have the wireless standard. In the middle, you have the modulation scheme that underlies the standard, which is what we're actually experimenting with. And on the right, you have the experiment, the name of the documented experiment that we have. So you will recognize a lot of modulation schemes that you'll be familiar with and that are very relevant these days. I'm just going to whiz through this and ask questions at the end, if you can please memorize this list. So that was a brief look at standards, and then we have a brief look at the various experiment listings that we have. You'll recognise all sorts of diverse topics, even delta modulation, I patterns, analog, introductory analog, advanced analog, block coding, frequency hop, sonnet, spread spectrum, ISI, equalization, MSK, all the constant envelope schemes, QPSK, ultra-wideband, spread spectrum, again. Bit error rate measurements are very important. As well, using this block diagram approach, we're able to expand into signals and systems. So students are able to basically build signals and systems experiments using the TIMS blocks. So just moving right along, we have more experiments, DSP. And basically, in summary, every unit ships with 2,500 pages of carefully documented experiments. And the point being that this is like a menu. You choose the blocks that you need to implement the curriculum that you're interested in. So you have the resources, the material there, and you just choose what you actually want to cover. And as you want to expand your curriculum, you simply add more modules when you need them. So here's another way of thinking about how you can chunk your experiments with the transmission model. You could teach encoding in one lab, teach decoding in the other lab, or just concentrate on demodulation, etc., etc. So how do we deliver these experiments to the students? There's three ways: hands-on in the lab, remote access, or simulation. So having a look at the various hands-on approaches, we have the TIMS, which we've looked at briefly. We have experiments in signals and systems where we're able to cover convolution, match filters, Fourier, Nyquist, poles and zeros, IAR, FIR structures, etc. All fully documented. So it brings this complex mathematical subject to life for the students. Okay, I might skip that video. Fibre optics, we're also able to have some introductory fibre optics subjects, so students don't have to go into your expensive fibre optics lab to do experiments. They can quickly do wave division multiplexing and bidirectional communications experiments with simple hands-on modules using optical components. We have a DSP option, so you can code up any blocks that you might need, Viterbi, digital filters, convolution, etc. We have a small unit, which I will hopefully... We have a small unit called Biscuit, which you can't see, so let's see if we can put up there. Which is a little mini version of TIMS where you have a limited number of blocks. So a more low-cost option and more portable option. Okay. So obviously at our booth we have all those options. And also NI recognised that what we were doing was quite interesting, and they invited us to make some boards for their NI Elvis platform. So 6 years ago we made the Datex board for teaching telecoms, SIGEX for teaching signals and systems, Photex for teaching fibre optics, and Helix for teaching hydrogen fuel cells and sustainable energy, all powered by LabVIEW if you happen to have an Elvis lab or are thinking about getting an Elvis lab. So a second approach, we have remote hardware. That's where we are basically able to deliver these hardware experiments across the internet so that students have that Java-based client and they interact with the hardware as if they're in front of the hardware by replacing the knobs and switches with electronic knobs and switches. You can have multiple students, from 20 to 60 students at once, doing the same hardware experiment and having it delivered across the internet 24/7. So this is very handy for MOOCs. We have a few customers using that around the world. Also for distance learning. I'll skip on that video. Finally, we have a simulation option because we believe simulation is very useful as a complement to hands-on hardware, particularly as pre-lab learning. It was a very interesting story a professor told me. He got a student to design a filter, and the student said, "Yes, I've done it." He said, "What did you do?" He said, I designed a 256 order filter." He said, "Oh, that's marvellous, you'll get 50% of the marks for that. Now for the next 50% you have to go and build that 256 order filter." So sometimes, simulation is very helpful, and yet we really need to know how that manifests in the real world. So with our simulation as pre-lab learning, the students don't have to do any programming. They plug the modules in, wire them up, and turn the knobs and dials and have a hands-on experience. It looks like that, and It's very easy to use and very complementary. And finally, so my take-home message would be TIMS is mathematical modelling with real-world signals. A block diagram approach is always relevant no matter what the underlying technology is. Multiple experiments in one system. It's expandable because it's open architecture. You can make your own modules. It's customizable and it's modular. It's highly student resistant and proven reliable. In the 25 years we've been manufacturing, we've never charged for a service because despite having thousands of units around the world, we only get a handful of returns every year. And so we're kind of like Rolls-Royce. You buy our equipment and it's there to last and we look after you. Students enjoy learning by doing. They like using TIMS and making stuff happen, making it smoke, as we used to say in the old days. It's deliverable by multiple mediums. It's MOOC ready. And the glass of wine there is to remind me to invite you to come down to our booth and enter in the draw, because I've bought an exquisite bottle of 2008 Shiraz from the Barossa Valley, and we'll be giving one of those away to somebody at the end of the expo. And I'd also like you to meet our American representative, Sheila Woodson, who can look after you and come and visit you. So thanks very much for your time. Lovely to be here, and come and see us.